Now we will study dynamic properties of single particle moving in one-dimensional potential. And let us consider, we will consider v of x, which is general enough to allow for the illustration of all the desired features. Now we will see when showing the equation in one-dimensional case. Now, this is the potential behavior, general potential behavior. And in this case, it is finite at x equal to plus or minus infinity. It is finite at x equal to plus or minus infinity. Okay. And v of 1, we can say that v of 1 uh, is equal to v of 1 is at v of infinity. Okay. And therefore, we can also say that v of 1 is related to v of minus infinity and v of plus infinity. We can say that this towards it. And therefore, we can say that v1 is smaller than v2. V1 is smaller than v2 and it has minimum minimum. And in particular, if you want to study conditions under which discrete and continuous states occur, as the character of the states completely determined by the size of the system. And this is the bound states under this region, and both these are the continuous states. Okay. And these are the conditions. And for x tends to plus or minus infinity, we will get v1 as well as v2. And this is the shape of terminal potential. This is the graphical behavior of v of x with respect to h. Now, the basic equation is given by 1, that is a minus h per square upon 2n k bar square divided square of psi of x plus v of x psi of x equal to d of psi with your meaning of meaning of symbol. That is the v of x potential and psi of x wave function is the v of x potential. Psi of x is wave function. D square upon dx square is the double derivative with respect to x. H cross is the reduced length constant, which is h equal to h cross equal to h upon 2. Now, you can see that based on this condition, we can explain the graphical behavior of potential with different position. Now, so equation 1 is from equation 1 we can say that E is the total energy of the system, and for equation 1, the Schrödinger equation for two timely independent potentials are stationary, and therefore general equation solution of general equation psi of x comma t is equal to psi of x e raised to minus r d e. And for the probability density, which does not depend on time, and therefore we can say that psi of x has the physical dimensions physical dimensions of 1 upon their elite length, and therefore physical dimension of surface, the dimension is about 1 upon root A, and therefore physical dimension of psi of x bracket here is equal to 1 upon root A of c, which is equal to, we can say that 1 upon okay, and therefore from this knowledge we can find of the wave function, and therefore next is from this we can write the discrete spectra. We can explain about the bound state. The motion of particle in the bound state is in between E equal to V minimum less than E less than E. We are aware of the number. And which this states correspond to the energy range is known as bound state. Okay. And therefore they are defined as states whose wave functions are finite at x tends to plus or minus E. And usually the bound states have energy small, always smaller than the potential, where we can say that E is less than. And for the bound state to exist, the potential of V of x must have at least one minimum which is lower than 1. Therefore, we can say that V1 that is V minimum is less than V2. And the energy spectra of bound states are displayed. And these are the different conditions, and therefore we can explain for theorem 1 and theorem 2. That is, there are two theorems. There are two theorems. Number 1 is related to energy levels. Energy levels of bonds and energy, and one more is there, that is which is based on the modes of this. Let's see. In case of bound state, these are the we can write properties of one-dimensional motion in terms of bound state, motion of the particle, and theorem. In case of a bound state, we can say the value of, that is, the bound states generally occur whenever the particle cannot move infinity. The particle cannot move to infinity. It is a bound state with limitations of energy, and that is the particle is confined or bound at all energies to move within a finite and limited region of the space. Okay, and Schrödinger equation in this region admits only solution that is discrete. And in this case, based on the diagram, we can say that V minimum is less than V minimum and V minimum. And therefore, we can explain the motion of the particle. And here, this is the state, and this state is called bound state. And therefore, we can say that it's into plus or minus infinity. We will get V1 and V2. For minus, you will get V1, and for plus infinity, you will get the V2. Okay, and the in classical turning points x1 and x2, when the particle energies x1 and x2 are in between V1 and V2. Then there are two theorems. Theorem number one. Theorem number one. Okay. In a one-dimensional problem, in one-dimensional problem, the energy levels of a point state of the bound state. The energy level of bound state are discrete and non are taken. Second is the first theory. There is a one-dimensional problem. The energy levels of bound state, the energy levels of bound state are discrete and non-negative, means binary. And second, the wave function in the second wave function psi n of x of one-dimensional bound state system has n number of modes, and that is psi n of x vanishes n times, vanishes n times if n equal to 0, if n equal to 0, which corresponds to the ground state, and n minus 1 and n minus 1 modes if n equal to 1, which corresponds to the ground state. And this is about the properties of one-dimensional motion. And we have already explained first for this, first write the Schrödinger equation, which describes the dynamics of the microscopic particle of mass n in a one-dimensional time independent potential energy. Based on that, write psi of x comma t, which is equal to psi of x e raised to minus e t upon x cross, and based on that, find out the length, physical dimension of psi of x bracket square, which is equal to 1 by a. Then draw based on the shape of the general potential. You can explain about the bound state. Then motion and bound state, explain about the bound state, what is the concept of bound state, then motion of the particle in between Vmin and V1 for x tends to plus or minus infinity, you will get V1 and V2. And then write the theorem, that is in one-dimensional problem, energy levels of the bound states are discrete and not frequent. And theorem 2, wave function sin of x of a one-dimensional bound state, this thing has a n number of modes. For sin of x vanishes n times, and if n equal to 0, which corresponds to ground state. And if n minus 1 modes, if n equal to 1 corresponds to 1. And it's about the Schrödinger equation in one-dimensional case. These are the properties of one-dimensional motion.